Today we're learning how to mathematically calculate Kc from a disequilibrium situation. We're learning this so that next chapter we'll be able to determine the hydronium ion concentration of weak acids. Our success criteria today are being able to solve for Kc using an ice table and solve for concentration when we're given Kc. So I'm going to show you how to use ice tables in some sample problems. But what an ice table is it's a way for us to relate initial concentrations to equilibrium concentrations and to our Kc value. So ICE is actually an acronym. It stands for initial, change, and equilibrium. Some people actually call them rice tables as well. They include the R at the top for reaction, but we set them up the same way no matter what we call them. So we use this to our advantage because it allows us to base our numbers off of the equilibrium values, but we're not always given the equilibrium values. So we can actually calculate what the equilibrium value would be if we're given the initial concentration. And that is what the initial change in equilibrium stand for. It's initial concentration, change in concentration, and the equilibrium concentration of all of our chemicals. And as we saw previously, we need those equilibrium concentrations in order to calculate a numerical value for Kc. Really important thing, because a lot of people make mistakes on this, is that when you do the Kc calculations, it's always going to be based off of your equilibrium or E row. You never use the values in the other two rows. We just use those two rows to figure out what the equilibrium value would be. We can also reverse ice tables, turn them backwards so that if we are given Kc, we can figure out what the equilibrium concentration of chemicals will be if we know the initial concentration as well. So we have a rule that we need to keep in mind. It's called the rule of 1,000, and what it means is if the initial concentration of the reactants is 1,000 times greater than the Kc value, then mathematically the change in that concentration is going to be insignificant. And really what that means is that even if we calculate what the change in initial concentration to equilibrium concentration would be, it ends up being a rounding error. The rounding error is actually bigger than the actual change, so it's difficult to measure, which means the initial concentration and the equilibrium concentration for mathematical purposes hasn't changed. So the rule of 1,000s we're going to see in the sample problems is really useful. It helps to speed up these calculations significantly, and it also means you don't have to use the quadratic formula. In Chemistry 30, if you end up using the quadratic formula, you have done something wrong. You don't get presented with questions in Chemistry 30 that require you to use the quadratic formula. You can solve them using the quadratic formula, but you don't have to, and that's because of this rule of 1,000.